Hey guys, this is Wes. Today I'm going to give a short, simple example of using DMA and an instance where we get a different result from the application when we use DMA and don't use DMA. So for the first part of the video, I'm going to quickly write an application that outputs song lyrics through PuTTY and at a certain interval. In this case, I'll do every 5 seconds. And what I want to happen is, in an infinite loop, I want to toggle the RGB LEDs so that they are just continuously going off and on within the main while loop. And as you're going to see, when we start outputting things over PuTTY, there's going to be a delay in the toggling of the LED since the CPU has to handle the toggling and the outputting, and it can't do both at the same time when we're not using DMA. So the first thing I'm going to do is think about which peripherals or which systems I'm going to be using for this specific application. And I know I'm going to use usart because I'm going to be outputting to PuTTY, and I know I'm going to use a timer because I need a delay of 5 seconds, and in this case I'm going to use an interrupt. So every 5 seconds I'm going to output the lyrics to PuTTY, and finally I'm going to use GPIO because I'm going to need to toggle the LEDs. So I'm going to start by including the UART.h file, which I already have in the project. And then the way I got those was by right-clicking here and going to add existing item, and then search for wherever you have the files, whichever they may be on your computer. So that includes UART. I'm going to use I said I was going to have a timer interrupt, so I need to include avr/interrupt.h. That'll give me access to SEI and the ISR macro function, etc. Okay, now that's out of the way. I'm going to go ahead and write a initialization function for the timer. So tc0 init. All right, and then because I'm only working with a single source file, I'm not going to make a separate pair of files just for the timer. I'm going to add the prototype above my main function and then define it down here. So the first thing I'm going to do is clear the count just in case, and then I'm going to set the period. So remember I said I wanted the interrupt to happen every 5 seconds so that I can output the lyrics. So I'm going to use the equation that we've kind of pounded into your brain at this point in the class. So the clock speed 2 megahertz times the delay or the duration divided by the prescaler. Okay, so that's going to end up giving me an overflow rate for the timer of 5 seconds. And then finally, I'm going to do int control A, you see overflow at level low. So this is enabling low level overflow interrupts for the timer on port C0, blah blah blah. Okay, and then I need to also actually start the timer. So tc clock select div 1024. There we go, and this is going to actually start the timer. Okay, and then in my main, I'm going to go ahead and do it now before I forget. But I actually need to call the tcc0 init function. Okay, next thing I'm going to do is, because I know that I want to use the RGB LEDs, I'm going to go ahead and, before I start my timer, I'm going to initialize those. So I know from the schematic that the RGB LEDs on the micropad are connected to port D. So I'm going to initialize them to be off by default. So port D dot out, and remember they're active low, so to turn them off I need to set them to ones. And I'm going to go ahead and demonstrate something in C. I'm going to create a define or a macro definition. I'm going to call it RGB underscore BM, and BM stands for bit mask, because what I'm going to do is I'm going to take the value that corresponds to the 3 LEDs, and I'm going to create a bit mask for it. So because I know they're on pins 4, 5, and 6, I'm going to do let's see, 0x7 shifted left 4. So what that's going to do is it's going to take a 3-bit value, like this, and it's going to turn it into this, where bits 4, 5, and 6 are set. Okay, and that's going to be my per se bit mask. All right. So now in my main, I can use that bit mask here. So what this is going to do is it's going to write X70 to the outset register, which is going to set the output values at the RGBs to make them off. And then port D dot dir set equals RGB bit mask. All right. So so now my RGBs are outputs and they're off by default. All right. So now the next thing I do is call my timer initialization, and then because I'm using UART, I also want to call my usart initialization, usart d0 init, so that I can communicate with PuTTY. And for this example, I've configured this to be a baud rate of 9600, so not too fast. Okay, and finally for initializations, I need to enable interrupts, because I'm going to use the interrupt I'm using is for the timer, so I have to enable them or it won't work. PMIC low level enable, because I used a low level for the timer, and then from the interrupt.h file I can use the SCI macro function. Okay, so that about does it for initializations. Now one more thing we can do is go ahead and write the ISR for the timer. So I'm going to use the ISR macro function, and then TCC0 overflow vect is the interrupt vector I want to be associated with this ISR. Alright, and the way I'm going to do this is I'm going to set a software flag in the ISR instead of outputting all of the lyrics within the ISR. Because like we try to stress, you want the ISR to be as short as possible. So I'm going to create a global variable, and in this case I'm going to make it volatile since I'm using it within the ISR. I'll call it send, and I'll set it equal to 0 by default. Okay, and then in the ISR, what I'm going to do is set it true, so that in my main routine, and this is going to look very similar to the accelerometer lab where you set a flag in the ISR and then you handled it within main. So I'm going to have an if statement saying if send is true, do something. Okay, and the first thing I'm going to do is set send equal to 0, and then in this case I'm going to have a set of lyrics, and those lyrics I'm going to define in an array. And by the power of post-processing, the array of lyrics has magically appeared. Okay, so the example we're using is a song called Rockin' Robin by Bobby Day. So we're just going to be outputting this small section of the lyrics to PuTTY every 5 seconds. Alright, now one thing that we need to do still is, one of the criteria for the application was to toggle the RGB LEDs as fast as possible within this while loop. So I'm going to go ahead and do port D dot out clear the RGBs, and then port D dot out set RGB. So this is going to turn them on, then off, and then the next time it goes into the while loop, it'll turn them on again and then off again. So all of the cycles of the while loop in which this doesn't happen, so all of the time in between the 5-second overflows of the timer where we output the lyrics, it should look like the LED is just toggling extremely fast. So fast that we won't really be able to see it. Okay, so the last thing we have to do is output the actual string or the lyrics every 5 seconds. So within the if statement, I'm going to do usart d0 out string, and I need to pass it a pointer to the first character in the string, which in this case, because we called the array lyrics, it also acts as a pointer to the first character. And then outstring is gonna output all the characters until a null character is found, and when we define a string in quotes like this in C, it automatically null terminates the string. Cool. So now if we build this to make sure we don't have any errors and it succeeds, then we can program the device. And as you can see on PuTTY, we're outputting the lyrics every 5 seconds approximately. And then if you also notice on the micropad, the RGB LED appears to be on the entire time because we're toggling it so fast that it's just going to look on to the human eyes. But you notice that every 5 seconds we get a little blip or a dip in the RGBs being on, and this corresponds to this section of code where it's outputting the string. Because you can see the string being output, there's a delay from the time it starts writing to UART to the time it stops, and that's the amount of time that the LED is being off for. So because the CPU can only handle one thing at a time, anytime we're outputting UART characters, we're not toggling the LED. So this is where DMA is going to kind of help, at least for this application, because what we're going to be able to do is handle the outputting of the string entirely through DMA, so that the CPU doesn't have to do anything except toggle the LED. So to start this part out, I'm going to go ahead and open up the manual and go to the DMA section. And then towards the end of the section, I'm going to go to the register descriptions. And now the DMA peripheral is just similar to the ADC. There are multiple channels that you can configure separately from one another, and the DMA just happens to have 4 channels. So there's some registers that configure the overall DMA peripheral, and then there's some registers that can configure each channel separately. So first I'll start out by going over the overall registers, and the first one we come up across is the control register. So the 2 bits 7 and 6, the enable and the reset bits, are the 2 we care about specifically for this register. The enable bit here will enable the entire DMA peripheral, not just each channel, but all of them, if each one is enabled, of course. And then the reset bit will reset all of the configurations in the entire DMA module when it's set to a 1. So the enable bit is something that we recommend doing at the end of your DMA initialization, because a lot of configurations will simply not work or not be put into effect if DMA is enabled. And then reset, conversely, we would like to do at the very beginning of our initializations, so we can start with a blank slate unless any of the registers have been modified previously. So I'll go ahead and start out by creating a DMA init function. So void DMA init. Alright, and then I need to add the prototype, like tcc0 init. Cool. So now the first thing I'm going to do is reset entire DMA periph, and then at the end I'm going to enable entire DMA. Okay. So in order to reset DMA, I need to write a 1 to the reset bit. So I'll do that by typing DMA dot control, and I'm going to or equal it with DMA reset, and this is the bit mask that corresponds to bit 6 being set. And or equal is equivalent to saying DMA.control ORed with DMA reset. It's just shorthand so you don't have to type the register name again. You can do it however you like though. It ends up being the same thing when it gets generated into assembly instructions. So now we're going to do the exact same thing except for the enable bit at the end of our initialization. So DMA.control or equal DMA enable. And it's important that we do or equal here because if we did care about any of the bits in these 2 bit fields, this would overwrite them if we didn't have the or. So make sure we have that. Alright, back to the manual. We have interrupt flags and status registers that are similar to other peripherals. just with respect to DMA specifically. Temporary registers. Now we're into the registers that are specific to each channel. So in this application, it's very simple, so we only need to use one channel. So I'm arbitrarily going to choose channel 0. There are similarly enable and reset bits for each channel, as well as bits that are specific to how we want to configure DMA. So whether we want to send multiple blocks per transaction, let's see, transfer request. This is a way for us to start a DMA transaction using software instead of other trigger sources that we'll see later. Single shot. So this basically means that you can send a single burst per transfer trigger that you come across, and then burst length defines how many bytes per burst: 1, 2, 4, or 8. So I'm going to similarly to the way I enabled the entire module, I'm going to enable channel 0 at the end of the initialization. So DMA.channel0.control A or equals DMA channel enable. And you get used to guessing the names of these bit masks and group configurations the more you type. Okay. And then I'm not going to worry about resetting it since I reset the entire system here. I don't need to. Okay, so the next thing we need to do is actually think about how DMA is going to be configured for this specific application. DMA is it's a huge peripheral with a lot of different combinations of configurations. So it's really important that you kind of boil it down to a specific pattern. So in this case, remember that we have an array of characters that we need to be transmitted from memory, or in this case, most likely SRAM, to a peripheral register, notably the UART data register. So with DMA, you always have to think about it like that, as a source and a destination. So you have a source, in this case the array, and then the destination, the UART data register. So after we have that, we need to separate it into the different types of, or the different pieces of data within a transaction. So remember, we have bursts, which is a certain number of bytes, and then we have blocks, which is again a certain number of bytes. And those together can encompass a transaction. So back to the registers, we're going to define a burst as a single byte, because remember, we only want to send one character at a time, because with UART, if we send multiple, then we could overwrite or lose data. And then the block is going to be the entire array, because every 5 seconds we want to send a single iteration of the array to PuTTY. We don't want to send, say, 5 of them. Okay, and then that block is going to be the entire transaction. So we're going to have a transaction of a single block with however many bytes are in this array, and we're only going to send one iteration of it. Okay, so that being said, let's take a look at some of the other bits in this register. So the repeat bit, we are not going to use, because what that would allow us to do is to send multiple blocks per transaction. So in some applications that may be necessary, but for this one it's not. Alright, the transfer request bit is a way for you to trigger a transaction via software instead of having a interrupt flag from another peripheral do it. So we're not going to worry about that for now. And then single shot data transfer, so the single bit, this is actually important because this says that a single burst will happen every transfer trigger. So if we do not enable this, then as soon as we get a single trigger, which in this application the trigger is going to be the UART data register empty flag being set. Okay, so back to what I was saying, a single shot data transfer means that for every transfer trigger we would send a single byte of data, which is exactly what we want. Every time the data register is empty, we want to send a single character. And then if it's not empty, DMA is not going to do anything. Okay, so if we did not enable this, then as soon as the data register empty flag was set, DMA would try to send all of these bytes sequentially without waiting for the flag to be set. So again, not what we want. So we're going to set the single bit, and then the burst mode bit field determines how many bytes there are per burst. And as we said earlier, we only want 1 byte because that corresponds to a character. So let's go ahead and configure this guy. So again, it's the DMA channel 0 control A register. Play. And we're going to say we need it to be equal to, remember we needed single shot and a 1 byte burst length. So DMA channel single, DMA channel burst length 1 byte. And that should just about do it for that register. Next thing we need to do is configure the address control register, which is down here. So this is one of the, if not the most critical registers when it comes to DMA, because like I said earlier, it all boils down to a source and a destination, and this register configures how the data is transferred from the source to the destination. So the order and what happens after, say, a block or a transaction is complete. So source reload, remember source is this array of lyrics. So the source address is going to be the address that corresponds to the first character, which we'll configure later. And then the reload bit field here says when does the source address reset to what it was originally configured to. So basically, we're going to initialize the source address to the beginning of the array, and then every trigger, the address is going to increment to the next character. And then after the entire block is done, and we get to the end, that's when we want it to reset to the beginning. So we're going to choose block for this bit field, because if we chose say burst, that means after each byte, it's going to reset, which is not what we want. It would just output the same byte over and over again. Okay, so address control, I'm going to go ahead and start writing this down. DMA.channel0.address control equals DMA channel, and then I'm just going to look at the bit field, source underscore reload, and block. So after an entire block is transmitted, we're going to reset the address back to that first character again, so that the next 5 seconds come by, we can start at the same place we were. Alright, now source direction. So this says, let's see, after each byte we transmit, or each burst, what happens to the source address. So, because this array is contiguous in memory, each byte's address is one above the next. So every time we get a trigger and we transmit a burst or a byte, we want to increment the address to get to the next character. So we're going to choose increment. So I'll OR that with DMA channel source direction increment. There we go. Okay. So that does it for the source. And now we have basically the same 2 bit fields except for the destination. So this is a lot easier because remember our destination is just the UART data register. So that's a single address and it stays fixed. We don't need to increment or anything like that because it's a single 8-bit register. So for destination reload, it's going to be none because we're never going to change it, therefore we never need to reload it. And then destination direction is going to be fixed because it's always the same address, so after each byte we don't need to change it at all. I'm going to do dest reload none, so DMA channel dest reload none, and then DMA channel dester fixed. Alright, so to summarize that, the source address is going to start at the beginning, and after every burst or byte, it's going to increment to the next character. And then after it increments to the end of the block and transmits all the characters, it's going to reset the source address back to the beginning. And then the destination, which is the UART data register, is always going to stay the same and never be incremented or decremented. All right, now we have the trigger source register. So this is going to allow us to configure the DMA transaction or burst or whatever to trigger off of other peripherals. So in this case, we want to use the usart D0 trigger. And specifically, we want it to be the data register empty flag. So DMA dot channel 0 dot trig source equals, and I just happen to know the group configuration for this, but you would be able to find it in the manual, of course, or the include file. So it is DMA channel trig source underscore, and you can see I'm already getting a list of all these different ones, but I don't have to filter through those because I know it. So usart D0, and you can see I could choose either the receive or the data register empty, and I want data register empty flag. Okay. So now that we got that, we're going to go ahead and specify the transfer count. So the transfer count is a 16-bit register that determines how many bytes there are per block. So we have to basically load that register with the number of characters in this lyrics array. And a nice easy way to do that in C is the following: dma.channel0.transfer count. Because it's a 16-bit register, I can just do the entire one. I don't have to do low, high, etc. This is a 16-bit register, so I'm going to typecast this to 16, a uint 16t, and then I'm going to use the size of function that's native to C, and I'm going to pass in lyrics. So what this is going to do is the compiler is going to determine the size of the lyrics array before it gets loaded onto the board, and then it's gonna equate that to the transfer count register. So we don't have to manually count each byte and figure out how many there are in the array. We can just use size of. All right. Now the next thing we can do is we have to actually initialize the source address and the destination address. So this is relatively straightforward. The source address is going to be the beginning of the array, and the destination address is going to be the address of the usart data register. Usart D0 specifically, because that's what's connected to USB. All right, and just like any other register that's greater than 8 bits, we have to load the low byte to the high byte. Okay. Which in this case means we have to do source address 0, 1, and then 2. Alright, so dma.channel0.source address 0, I'm going to set that equal to lyrics. Okay, lyrics. Okay, sorry. Now, this is fine for the most part, but if I build this, well, first of all, I forgot a semicolon. Expected blah blah blah. Okay, no, I forgot an or. There we go. So now if I build this, it's gonna build, except I'm getting a warning. Because of the way I'm doing this. Because lyrics is a pointer. It's a pointer to a character, because it's the name of our array, so it's pointing to the first character in the array. And the source address register is an 8-bit register, but it's not a pointer. So it's just complaining that it makes integer from pointer without a cast. So what I'm going to do, just to make the compiler happy, is first I'm going to cast it to a uint pointer type. And basically all this type is, you don't really need to know about it for this class, but it's just a way to do arithmetic with pointers. So what I can do after that is cast it to an 8-bit type, because the register source address 0 is 8 bits. And now when I build, I don't get any errors or warnings. Okay, so this is not necessary. It just suppresses the warning, which is good practice. So now I'm going to do similar. I'm going to do the source address 1 register. So I'm still going to cast it to an 8-bit at the end. But the difference is now I need to get the second byte of the lyrics pointer. So to do that, I'm going to shift the lyrics pointer to the right by 8 bits. So I'm going to again cast it to a UART pointer type, lyrics, and then I need one more parentheses. I'm going to shift that to the right by 8 bits. And then, let's see. And then I'm going to try to build one more time, see if I get any warnings. Missing a parentheses somewhere. Need one more here. Okay, build succeeded, good to go. Now I'm going to go ahead and copy this line, change the 1 to a 2, and I need to shift this over by 16 bits because I need the third byte. So let's build that. I just want to make sure I don't get any warnings. Right shift count greater than or equal to width of type. Alright, so now the problem is I have this, but it's being treated as a 16-bit value or less. So it's complaining because if you shift a 16-bit value to the right by 16 bits, you just get 0 because there's no bits to shift in. So what I'm going to do is before I cast it to a UART pointer, I'm going to cast it as a UART 32 because the UART 32 would give me plenty of wiggle room when it comes to shifting by 16 bits. So bear with me while I fix my parentheses. UART pointer, and then I need one more parentheses here. Alright, now I can build that. And I guess I have an extra parentheses somewhere. 3. Yeah, I don't need that guy. Okay, so now I've successfully loaded the source address, and again, a lot of this is not required, it just suppresses the warnings, which I think is good practice. So we're going to do basically the exact same thing for the destination address. So I'm going to copy all of this just to save time, shift it over, and then I need to change everywhere it says source to dest. And I also need to change the pointer to, instead of lyrics, it needs to be the usart D0 data register. So what this ampersand does is it returns the address of this register. There we go. Okay, good with that. So to summarize, we have the source being our lyrics array and the destination being the UART data register. Cool. Now the next thing we need to do is enable the channel, which we've already done here, and that should be it for the initialization. So this may seem like a lot, and it is at first, but once you understand the dynamics of the source and the destination and how to come up with a strategy as far as whether you should use single shot mode or not, how many blocks you need to send, etc., it's really not that bad. The hardest part is just kind of taking it all in and realizing how many different combinations of configurations there are for DMA. Okay, so now that we have DMA initialized, I'm going to go ahead and call the function here, DMA init, and then we need to rethink how the main routine is going to be structured. So now we no longer need this entire if statement because UART is handling all of this on its own. So I'm going to get rid of it. And now the only thing that the CPU is doing in main is toggling the LED. And then the next thing we need to rethink is the timer ISR. Because now every 5 seconds we no longer need to set this variable since the variable is not being used. But instead we're going to actually enable DMA so that if the data register empty flag is set, we can start sending bursts automatically. So when I say enable DMA, all I mean is setting the control A register like we did in the initialization. Excuse me. There we go. All right. Now additionally, because the trigger is the data register empty flag, DMA won't necessarily start as soon as we enable it. We have to kind of kickstart the process by using the transfer request bit that we kind of skimmed over earlier. What I mean by that is this guy, transfer request. So this will start the transfer of data, and then after that, every time the data register empty flag gets set, DMA will handle it all automatically. So DMA.channel0.control-A, DMA channel transfer request. And there we go. So now, to summarize the entire program, the only thing that CPU is going to be handling in main is toggling the LED. And then occasionally it'll have to handle the timer interrupt. So one time every 5 seconds, the CPU is going to have to run, less than 10 instructions most likely to actually kickstart the DMA process. And then every time the data register empty flag is set after that, we're going to be sending a single character over UART. So I'm going to go ahead and build one last time to make sure there's no errors. And I'm going to program the board and check PuTTY. This is maybe from last time. And there we go. So now notice that we're still getting the lyrics output every 5 seconds, but if you look at the LED, we're not seeing it toggle anymore. So because we got rid of the requirement of the CPU to use outstring to output the entire array, DMA is doing it in the background so the CPU can focus on toggling the LED. So I know this was a very simple example because we're just toggling an LED and outputting a string, but it really demonstrates that you can solve some problems, however simple or complicated they may be, by implementing DMA into your application.